This tutorial is going to look at intermolecular forces for A-level chemistry. Here we're going to focus on induced dipole-dipole interactions. This is the weakest of the three intermolecular forces that you need to know about for A-level. Now what I've drawn for you here is two helium atoms, and I'm going to use this to show what actually happens in the induced dipole-dipole interactions, and then we're going to look at how this affects the boiling points of different molecules. Now you can see here I've drawn the outer shell electrons for two helium atoms. Now, electrons, as you should know by now, are not stationary. You find them in orbitals, in the SPD orbitals. So they are constantly fluctuating and they're constantly moving. At the moment, the electrons are evenly distributed on these two helium atoms. Now let's just say, at any moment in time, that these two electrons become unevenly distributed and they suddenly appear on one side of the helium atom. Now for a brief moment in time, that means that this side of a helium is going to be slightly negative, and this side is going to be ever so slightly positive. Now this is where the induced part comes in for the dipole interactions. Because if this helium is slightly negative on this end, and this one is slightly positive here, what it'll effectively do is induce a dipole in this helium. So these electrons will then move around to form a dipole in this helium atom, a temporary dipole. You then have an attraction between these two helium molecules because we've got the delta positive this side, the delta negative this side. So we've got opposite charges on our helium atoms because the electrons are now unevenly distributed. So there's now an attraction between these heliums. Now this happens throughout the collection of atoms within the gas. This is only temporary, so this is a temporary dipole, and at any moment in time it could break down and the electrons could reorganize in a different configuration or in a different movement. So they could move to different sides of the atom. And then the dipole disappears and then this attraction no longer exists. Let's have a look at a couple of examples where this is really, really important. Now, the first example we're going to look at is with two chlorine molecules. So I've got two chlorines here. Now, these two chlorines are not polarized molecules, so they won't have an attraction in general. However, because we've got electrons in here, there can suddenly be an uneven distribution of electrons. So let's say that the electrons move more to this side than they do to this chlorine. That means this will be slightly negative and this one's slightly positive. And exactly the same way as with the helium atom, that will then draw the electrons to one side of the chlorine molecule, making this side slightly negative and this side slightly positive. So again, you get a slight attraction between these two chlorine molecules. Let's have a look at another example, but this time we're going to look at bromine. So we've got two bromine molecules here. Now the exact same reasoning applies. Let's say that this bromine here draws the electrons more towards itself than the other one. You'll get an uneven distribution of electrons more towards this end, inducing a dipole in this bromine molecule. So that's slightly positive, that's slightly negative, so that one's slightly positive. Again, you get an attraction here between these two opposite charges. So these brief induced dipoles, they'll attract each other in these different molecules. Now, the difference here is that the number of electrons is really, really important. Now, it should be quite obvious here that the chlorine atoms are smaller than the bromine atoms. Now, chlorine, each atom has 17 electrons, so that equals 34 electrons in total. So there's 34 electrons in that chlorine, there's 34 electrons in that chlorine. If you look at the bromine has more electrons. It has 35 electrons for that bromine, another 35 for that bromine, so there's 75 electrons in here. So we've got 34 electrons for this chlorine molecule, but we have 70 electrons for this bromine. Now this is really, really important because the bromine having more electrons means that the induced dipole-dipole interactions are stronger than they are in chlorine. So the more electrons there are, the stronger the induced dipole-dipole interactions are because the shift of electrons is greater. So this is going to be slightly more negative than this one here is, because there are more electrons moving in the bromine. Now that happens as you work down the group. As you go down group 7, the number of electrons increases. So chlorine has more electrons than fluorine, bromine has more than chlorine, iodine has more than bromine. As you work down the group, you get more electrons for the atoms. Therefore, there are more electrons in the molecules as you work your way down the group. So the induced dipole-dipole interactions get stronger. Now let's look at these 3 and see why it's really, really important. So if we look at these different examples, we'll start off with fluorine. Then we go down to chlorine, bromine, and iodine. We can then look at the melting points, the melting and the boiling points. So if we look at the boiling point of fluorine, it is minus 188 degrees Celsius. The boiling point of chlorine is minus 34 degrees Celsius. The boiling point of bromine is 59 degrees Celsius. And then the boiling point of iodine is 184 degrees Celsius. So it's quite clear looking at the different boiling points that as you go down group 7, the boiling point quite clearly increases as you go down. Now that, again, just to repeat, is because the number of electrons is increasing, so the induced dipole-dipole interactions become stronger as you move down group 7.